be looking at the introduction to the rate of change when dealing with functions. Of course, there is of course the rate of function, the rate of change when dealing with the real life application like velocity and acceleration. You know the average change between the two. Now, in this case, let's look at the average rate when dealing with functions. Now, here on the screen, I have a straight line function. Okay, now we know in the straight line function we have what we call a gradient. Now, another term that they might that can be used rather is a slope. When they say find the slope, don't be confused. Slope and gradient are basically the same thing. Yeah, so the slope in that case, or rather gradient, gives us the rate of change of one variable with respect to another. Now here we notice that our gradient is equal to y2 minus y1 all divided by x2 minus x1, right? Make sure you do not interchange these the values, right? So whenever I start with point B, the y value of point B, then I will also start with the x value of point B. So this doesn't always have to be y2 minus y1. May confuse, it can also be y1 minus y2 all divided by x1 minus x2. So all that matters is basically you're plotting this your variable, or plotting your numbers correctly, right? Whenever I start with point A, then I should start with the y value of point A, and then the x value of point A in that case, right? It doesn't matter in which point you start with. Now here, calculating the gradient of a straight line, it's easy because you're basically using two, right? You're basically using 2 points that are most likely to be given on your exam. Of course, they will be given, and then we know that the straight line function is given as y is equal to mx plus c, where the m is what, of course, known as the gradient, and then c is my y-intercept. And then, of course, to calculate the y-intercept, you will either use point A and point B, or rather point B, and substitute the y value there and then the x value there. So that is easy, right? That is easy. So the main topic here is the gradient, right? The thing that I want to talk about mostly is the gradient. So calculating the gradient on a straight line function is rather easy because you're using 2 points. But how can we determine the gradient of a straight line function on a curve function, or let's say the parabolic graph? Let's say a parabolic graph, to be more specific. Let's say, okay, we have this let's say the function like that. What am I doing? Okay, let's say we have a parabolic graph that looks something like that. Okay, so how can I determine the gradient at that point there, right? Or how can I determine the straight line? Oh my goodness, how can I determine the straight line? Oh my, I'm sorry about that. Let's say let's say the point touches that graph once, right? How can I determine the equation of the straight line function here, right? How can I determine the equation of the straight line there, or how can I determine the gradient of this slope right there, right? Remember in that case, remember in this case here, whenever we want to determine the gradient of a straight line, we basically use 2 points, but in this case 1 point. In most cases here, they will only give you this point here on the graph, right? So you have to determine how you calculate the gradient in this case of the straight line there. Well, thanks to calculus, we can calculate the gradient of that slope using calculus, of course. But I just want to derive equation to show you how we get to that point of deriving, or rather getting this slope, or rather gradient of that line there. So in this case, of course, we are not given 2 points, we're only given a point, but the question is, how do we calculate the gradient of the straight line if we're only given 1 point? Remember, gradient is also an average between 2 points, right? We said that gradient is equal to you said that gradient is a change in y divided the change in x, right? Which gives us y2 minus y1 over x2 minus x1. Remember, it's a change between 2 points, but in this case we only have 1 point. Now how do we calculate the average, rather the gradient on a point of the parabolic graph, right? Okay, let's say we remember that y is also the same as fx, right? Remember that y is the same as fx. So let us change this form here to a functional notation. Let's say y is equal to fx. Therefore I will say, well, delta y, or rather delta fx, remember that fx is the same as y, and then I'm going to say, well, divided by the change in x, which is equal to in this case here I'll have fx2. Remember that point x2, right? To find the y value of x2, you substitute that point on your on the value of x, right? You find that point on the value of x, so you're gonna put x2 there minus fx1 all divided by x2 minus x1. Well, this didn't take us anywhere, right? Remember, we still need 2 points on the graph, right? Okay, so if we need 2 points on the graph, what if I introduce a line that cuts this parabolic graph, a line that touches this parabolic graph twice, right? So that we'll have a point there and we'll have a point there. But this is not a tangent in this case. Remember, we said that tangent is a line that touches the graph once. So a line that cuts the curve function in this case twice is what we call the secant line, right? This is what we call a secant line. So a secant line is basically a line that cuts the graph. You can see that this one cuts the graph and it touches this point 2 times, right? It touches this point 2 times. So the second graph basically is a line that is allowed to move along a curve, right? It's a line that is allowed to move along a curve, so it can be there as long as it touches the graph, rather as long as it cuts the graph or touches the graph 2 times, right? So this line, it rotates to a limiting position, right? It rotates to a limiting position. Okay, so now let us assign this point. Let's say this point here we have let's say point A to be x1 and x2, right? And then here not x2, y1. Then here we have point B to be x2 and y2, right? So remember, now we have these two, so meaning that this point here will be x2 and this point here is my x1, and then this point here is what I have as fx. Remember, nope, what am I doing? Okay, so this is fx1, and then this is another fx2, and this will be fx1, right? This point here would be fx1. Now in this case, what I can do is we will say, well, let's let the distance between these two values there, or rather x minus 2, let's let x minus 2, or rather x2 minus x1 equal to h, right? Let's let x2 minus x1 equal to h. Let's see what goes on then. So if you let x2 minus x1 equal to h, then we could notice that, okay, x2 is equal to what? Is equal to h plus x1, right? So if I substitute back into this original function, I'll have, well, delta fx over delta x is equal to, well, x2 is that, so meaning I'll have h plus x1 minus fx1 all divided by x2 minus x1 is basically h, right? So now if we say that x1 can be any value, or rather can be any x value, can be a point there, can be a point somewhere there. Remember that the second line, it can rotate. It's a line that is allowed to move along a curve, so it can be at any point. So let's say we will have x plus h minus, instead of saying x1, we'll say x, because x1 can be any x value, so I'm just going to put x and then minus fx all divided by h, right? So this formula now, this formula, it seems familiar, right? Whenever you guys are doing calculating the derivative using the first principle, you will use this formula here. It should be familiar with you, right? So this is a formula now that we use to calculate the gradient at a point, right? So now the gradient between 2 points will not be considered to be a constant line, right, as what we did here. This one was a constant line, so basically that means I could have used any 2 points. I could use any 2 points on the graph here and still get the same. I can use any 2 points on the graph and still get the same gradient, right? I could have used any point and still get the same gradient using any point on the straight line. But for this one here, the gradient, for using the gradient there, rather using the x value here will not be the same as the x value there, will not be the same as the x value there. So meaning for this one here, it is not a constant line, right? It changes when 2 points also changes, right? Whenever 2 points on the graph changes, also the gradient also changes, of course, right? So for a curve, we will call this the average gradient of a curve, right? It's called the average gradient. So whenever they say calculate the average gradient, is basically you calculating the gradient, right? It can be on a straight line also. We can say here calculate the average gradient. It's basically calculating the average, calculating the gradient. The word average basically means between 2 points, right? Between 2 points, right? Whenever they say calculate the average gradient, it's basically calculating the gradient. So when you want to calculate the gradient at any point on the parabolic graph or any other curve for that matter, you will need to find the gradient between 2 points, and we will need to find the gradient between 2 points, and then of course you can see that the distance between these 2 points, what happens is that they will keep on decreasing, right? They will keep on decreasing uh, we want the distance between those 2 points to be um, to be to become smaller and smaller rather than gradually increasing, right? So you want these distance to be smaller, right? You want this gradient to be smaller, and hence when they become smaller and smaller, what do they approach? Well, they approach zero, right? When they become smaller and smaller, they approach zero. So meaning that x2 minus x1 equal to h will approach zero in that case, right? It will approach zero, and hence in that case we will have a gradient of any tangent line on the of any tangent line on the curve function equal to the limit, because we are limiting this we are limiting our distance to be to becoming smaller and smaller, right? You want to see what happens in that case when it becomes smaller and smaller. So it will be the gradient as a tangent line, or rather the gradient will be the limit as h approaches zero of fx divided by change in x, right? Which in that case would be the limit as h approaches zero of the function f x plus h minus f x all divided by h. So I hope this makes sense here. This will be the gradient of the tangent line in that case on a curve. So whenever you have a curve and they want you to calculate the gradient, or rather the function, or rather the for you to calculate the, or rather to determine the equation of the function, of course is given as y is equal to mx plus c. To find m, then you will have to use this formula here. This formula here is very important whenever whenever you want to calculate a gradient on a curve. You will have to use this formula here. I hope that this makes sense, and on another video we will be looking at some examples on how to calculate the average gradient, of course, some applications, and yeah, I'll catch you on another one.